Let's begin. Put your names up, please, and we'll do some business first. So your second TA, your other TA, Turan, is here today. He's sitting over there. We will start. Yeah, good. Thank you so much, Turan. He will be running 2 of the 4 help sessions. There's no need to have help sessions this week. The first homework assignment will go out this Thursday, I promise. I want it to be a good use of your time. And I know it feels like we've been dragging our feet in the beginning, but that gives you some time to catch up with your other courses. Soon enough, we will be catching speed of light. I want to finish with numerical measures of numerical descriptions of data this week, so we can start probability next week, obviously. And I have a little issue with posting the slides before coming to class, and I know that is helpful to so many of you as you take notes, as you watch the slides, as you watch the lecture. At the same time, I literally change these slides every time I teach the course again. You notice, compare slides from this year to last year, they're very different. I keep changing my slides every year to stay up to date, to put fresh content, to change as my perspectives change and understanding changes. And oftentimes it's like 2 minutes before coming to class, and I'm making edits to the slides to convert them to PDF, copyright them, and put them on Canvas. That typically takes me about 10 minutes, and I actually don't know how much I will cover of these slides. So that's been the challenge here. So if you have a solution, please come and talk to me and tell me, why don't you do this? And everybody will be happy. What I will attempt doing moving forward is I will post whatever I think I will cover. I call it part 1, part 2, part 3. But then you take notes on it, and then I change it possibly when I go back to my office because I find a mistake or something like that. So I don't know what's the right answer. I know ideally you want to have access to the slides before coming to class. But if in most cases you will not, I just don't want you to hold that against me, please. Okay, I'm trying to get the best and most fresh content to you, but I will try to just upload at least what I think I will cover. It might not be complete. If you want to take notes on it, take notes on it, but then make sure you get the latest version that I will post essentially by the end of the topic that we're discussing. Okay, is that okay? Do we have an agreement? I think that's reasonable. And again, if you have a solution for this, if you've seen other professors who figured this out, please let me know. But I do change my slides significantly from year to year and from lecture to lecture. So I go back today and something I didn't like about the colors or the animation, or I found a mistake, I will change it. So, I'm gonna have to keep updating things, and then that, if you already took notes on the slides, they're not gonna be consistent, etc. So that's the reason behind this, not some mysterious reason I'm not posting the slides before coming to class. It's because I'm dynamic. I'm not just kind of repeating the same thing year after year, okay? Last time we started discussing numerical descriptions of data, and the first one was measuring the center of the data. And there are 3 measures of centers that we will discuss: mean, median, and mode. And we started with the mean value, or the average. And remember this sentence here because it will show up later. And if you took numerical methods with me, or listened to my discussion in numerical methods about regression specifically, I claim that the mean or the average value is oftentimes the most likely statistic that someone will report for a bunch of data. You want to understand how much you're spending on electricity, you take the average, how much you spent last year. You're on a pay plan for your gas bill, they take the average of last year. You want to report how much you're spending on food, you take the average of how much you're spending on food, because the average is indeed the simplest and easiest statistic to report. And it so happens it is a measure of the center of the data. And we talked about the difference between sample and population. We're referring to sample x1 to xn, same for population, but notice the difference between the subscripts, lowercase n and capital N for the population, lowercase n for the sample, to designate that this is not as big as a population. And in NumPy, in Python, as we Pythonify this, we call a simple numpy.mean, and that gives you pass it an array of data. This could be a list or a numpy array. Numpy does the job internally. It has to have numbers in it. It cannot be objects or like strings or text, and then it will take the average. And we left off last time doing this first coding activity, and we decided to adopt the count as our mascot for the class because we're counting things in statistics. And then I asked you to just open up a Jupyter Notebook. So let's open that up. Download these files. These contain data. They're on Canvas on the module called Numerical or Graphical Descriptions of Data. They're published. You should be able to download them. Make sure you put them next to your Jupyter Notebook so we don't have to go through a nasty kind of figuring out the directory structure where they are. So if they go in your downloads folder, move them manually to where you are creating your Jupyter Notebooks for the course, okay? Most of you did that last time. I'll ask you to do it again, and we will load up these data. This is very simple, loading up with NumPy. We're not doing any fancy Panda stuff or any advanced stuff with more complex data. This is just simple, one column of data. If you open it, it just contains a column of values, okay? So last time, I'll repeat this. And for those in the back, you guys okay? Can you see? Good? Perfect, thank you. I referenced this boilerplate that I recommend you copy from notebook to notebook, so you don't have to worry about it. This will guarantee that you create scalable vector graphics, good quality graphs that you can export as good quality and just use. And we loaded up the data. We typed in data numpy.load.txt, and you can do autocomplete here. Let me show you. Let me run this again. And then data, I went and said mp.load.txt. If you press tab, it will autocomplete, as you obviously know. And then if you open up the single quotation mark and you type in uniform data, it's going to suggest it if it finds the file right next to your Jupyter Notebook. It is not going to look elsewhere outside the directory. It's not going to find it on your Google Drive or on your downloads folder. Only if it's next to your Jupyter Notebook, it will find it. And then press tab, close the quotation, and then load it. Now we have the data with us, and then you can print the data. It's just simply an array of values. As the name designates, this should be uniform data, and we can verify this by plotting a cute, pretty beautiful plot with the histogram, and it just shows us that, yeah, the data is uniform, and it ranges. So remember, you're flipping the meaning of the y-axis and the x-axis with the histogram. The actual values of the data are on the x-axis, so the values from 0.1, they range from 0 to 1, actually. Those are the actual values of the data, and the y-axis is reporting the counts. Okay, how many values do we get between 0 and 0.1? How many of these data points? There's 1,000. Here, there's probably 900, etc., and so on and so forth. Now, I asked last time, what is the mean? Is it the average on the y-axis or on the x-axis? It is going to be on the x-axis, as you all answered correctly also last time, because we're finding the mean value of the data. The data go from 0 to 1. The mean value should be around 0.5. Okay, so it should be right in the middle over here. That's why we call it measure of center. And then you type simply np.mean, and you pass it data, and it gives us 0.49648, etc. Now we can do other data as well. Another data, mp.load.txt. So let's see. I have a bunch of these guys here. I have what is it? Normal distribution. Yep. So let's look at normal data.txt. Okay. You can explore the other data sets. I know I set them in the coding activity, but we'll just do 2 of them. And then again, when data is at hand, plot it to understand. We do a histogram on our data, and then you get something like this. The data ranges from -1 to maybe 6 or 8. And you can look that up if you take the min and max of the data set. We'll talk about that a little later. But the data looks like this. You can increase the number of bins if you want. Just take it easy. We do maybe 30 bins. and then you'll see more of this shape of the distribution. It does resemble the normal distribution that we discussed in the previous chapter, and this one is generally symmetric. So again, we expect the mean on the x-axis, and it's going to be right in the middle because this is not skewed to the right or skewed to the left. If the data were skewed to the right, there's going to be more weight on data to the right, to the left, same to the left. So we can compute the mean value as well, simply as numpy.mean, the data. Okay, so what do you think the mean is going to be here? We're going from probably -1 to 6. Let's see, data. And it's about 2.33. So right here, right in the middle, it is right in center, in the center. Okay, it's like the center of mass of the data. Let's do one more data set, but this one is skewed. And let me check what I called them. Go away. This thing keeps coming. Okay, so the other one is we'll do a right skewed data, p.load txt, and we'll do right skewed data, then plt.hist. So keep these cells separate because we're going to come back, we're going to compute other quantities on those data, okay? So just keep these cells open, don't override them. Bins equal, let's do 30, and if we do this, you're going to get this right skewed data, okay? It's got a long tail over here. There's a lot of data over here. Now, the mean is a center of the data, but it's based on the count. So what do you think the mean is going to be here? So if this data goes from 0 to 10, approximately, is it going to be 5? Or is it going to be closer to where the weight is? Think of the mean value as the center of mass. Okay, so think as if you're dropping balls on a scale. There's more weight on this side than there is on the other side. So the mean value is going to be closer to where the heavy data is. Okay? Sorry, not where the heavy data is. So let me see. P.mean data. Oops. Never mind what I said. My bad. Okay, so the mean value is going to be, it's 1 over here, right? So because think of it as the center of mass. There's more weight over here, although there are outliers over here, okay? But the mean is being affected by these data over here, okay? So let's do, we don't have to do, you can do the other three. There's bimodal and left skewed data. There's another 2 that you can do. Now, you can also plot where the mean value is if you want as a little trick. So let me show you this. I'm going to cut this and put it here before I plot the histogram. And I'm going to put this, average is equal. And then I will plot the histogram. But then on top of it, plt dot. If I want a vertical line, it's called an XV line, and that is going to be at the X. So if you put the XV line, this is going to plot a vertical line at a specified X value. The X value here, I want it to be the mean value, which is the average. And then I'm going to make the line color black or red, and then I'm going to do the line style dash dot, let's say. Okay, just to make it a little visible. And then what this will do, it will plot a line on where the mean value is. Okay, where the mean value is. Okay. Now we will later see plots where you know where the mean, where the median, and other properties are. But that's how you plot them on your graphs. Now the next variation to the mean, we're still with the mean as a measure of center. The next variation is called the weighted mean. Now this becomes important when you don't have full access to the data, but instead you only have the frequency distribution. And it's also important when you're computing other things, as we will see in the example. So it's a more of a generalization to the mean value. And the idea is that some quantities, some measurements carry more weight than others. So let's say you have a temperature sensor that in some cases it measured 10 data points within 1 hour versus 1 data point within the other hour. So there's 10 data points in that first hour, so we're going to give more weight to those data than the other measurement. There was one measurement in that 1 hour, right? So you have more samples in the first hour than there is in the second hour, so you need to weigh your average if you're calculating the average temperature in that case, for example. Okay, so the formula is very simple, is that you would have weight for each value in the data. You could, for standard data, for a standard mean, all weights are 1. But in general, not every data point is going to have the same weight, so you're going to have an array of weights of the same size as your data. That's the general case, right? They might all be 1. Some of them might be 1. Some of them might be larger than 1. Some of them might be less than 1. It depends on the situation you're working with. But again, we distinguish between the mean value of the weighted mean of the sample and the weighted mean of the population. And we still use the symbol x bar for a sample and mu for a population. But to designate that this is a weighted mean, we put a subscript w to say that has weights on it. Okay, the data points that we've collected have weights on them to not bias the data, to make sure that we're measuring things correctly. And then it's simply the same way as you did with the previous formula, where we did the arithmetic average of all the sample values or the population values. Here you're weighing them with the individual weights. So x1 has a weight w1, and then x2 has a weight w2, and so on, and you multiply those, sum them up, and divide also by the sum of the weights. This formula is a general case of the previous formula, where in the denominator you had n, right? If all the weights are 1, summation of all weights is going to be 1 plus 1 plus 1 plus 1 is going to be equal to n. So you'll get summation of xi over n, so which was the previous formula. I'll give you an example. So you drove 81 kilometers at 35 kilometers per hour and 40 kilometers at 51 kilometers per hour. What is your average speed? Okay. Your average speed is not 35 plus 51 over 2. No, because you spent more time, more kilometers driving at 35 kilometers per hour. More time, more kilometers driving at 35 than you spend driving at 51. So the weight, there's going to be more weight to the speed at 35 kilometers per hour than there is at the 51 kilometers per hour. And in this case, you would do a weighted average, and you say, okay, my average speed is the 81 kilometers times 35 kilometers per hour, and then the other one is 40 kilometers times 51 kilometers per hour over 81 plus 40 kilometers. And then you'll get the units in kilometers per hour, which is your average speed would be 40.3. You see, it's very close. It's closer to the 35 kilometers per hour than it is to the 51, because you spent more kilometers driving at 35 kilometers per hour. All right. In NumPy, you don't use the mean. There's a generalization of the mean value, which is numpy.average. So you can use numpy.average to compute the mean, but you cannot use numpy.mean to compute the weighted mean. Okay, the numpy.average generalizes the idea, and then you pass a data and a bunch of weights. The weights is an array of the same size as your data, okay, because each data point needs to have a weight. Okay, each data point needs to have a weight, and you pass those, and it just works out. Another example, sensor measurement. Temperature sensor measured the following data. Let's say measured 20 degrees Celsius, 20 times, that's like a frequency, right? 21 degrees, 180 times, 22 degrees, 120, and so on. So those are going to be our weights that we will use to compute the average temperature. And that's what you will use to compute the true mean of these measurements. 20 times 20 plus 180 times 21. And remember, you have to identify what is the weight and what is going to be what are the weights and what are the numbers. So the denominator here is wrong. So that's why I'm going to go and change that. The denominator needs to have the weights in it. which are the counts, 20 plus 180 plus 120, and so on. Okay, and like I said, every time there's a green slide, it's optional. You can work it out as an extra exercise. So this is an example that shows you can, if you know the mean value and you know some data points, like let's say, like this example says, okay, you spent $10 on buying, video games on Steam, and then, 2 of the video games cost $6. What did the last games cost, etc. And you can just subtract and figure that out using the mean value. So that's an example also in the textbook. It's just simple arithmetic. Okay, now here's an interesting situation when you do not have all the data, but instead you have counts like the temperature sensor example I gave you. I'm going to build on that, give a more serious example. So what if you only had a frequency distribution? So you only had bins. So from 1 to 2, and this is how many values I had. From 2 to 3, this is how many values I had. You only have counts. You don't actually have all the data that all the original data. You only have a frequency distribution or the histogram of the data. How would you calculate the mean? Right? When we ran with NumPy, we did NumPy.mean of the entire data. But what if you only had the bin edges and the counts? How would you compute the mean value? There's an idea to do this. So I'll take the early career salaries we did last week. If you remember, we had early career salaries for those with a bachelor's degree. That was the original data. That was the true data, $5,700, $53,000, etc., all the way to $82,700. And the true mean of that sample, you just sum them up, divide by the number of entries, you get $67,468. Okay? But what if you didn't have access to those data? What if you only had access to the histogram or the frequency distribution? What I told you, okay, all I know is that there are 3 individuals who make between $50,000 and $55,000, and then no individuals between 55 and 60, 6 individuals between 60 and 65,000, and so on. How would you get the mean? How would you get the average salary? Yeah, you have an idea?
You just take the average of each bin range.
Bin. Okay, how would I take the average of the bin?
Frequency, so you would add the bin edges together and then divide by 2.
So you're finding the midpoint of the bin. Yes, and that would be a what kind of mean? A regular mean or a weighted mean? A weighted mean. What are the weights?
The weights are going to be
the counts. Okay, exactly. Very, very well. Thank you so much, Alex. So what your colleague is saying is that, one idea would be, okay, I don't know. Remember, the mean value is going to be in dollars, not in counts. It's going to be on the x-axis. So the mean value is going to be in dollars, and we just don't know where, for all I know, the 3 people between 50 and 55,000, they could all be $51,000. Okay? Or they could all be, $54,000. But I know for sure that they are between 50 and 54. So how do you estimate the average there? You just, without any extra knowledge, take the midpoint of that bin. Could you take a third? Yeah, you can take a third. Still going to be an approximation. Could you take 3/4? Sure. But the midpoint is the best estimator for getting an average for each bin. So if we were to take an average for each bin, so the first one is going to be what, 52,500, the second one is 57,500, and so on. So that's going to give us an average value with counts. Okay. Now, how do we get the total? Remember the problem with the driver, 80 kilometers, etc. So there is 3 people at 52,500, 0 people at 57,500, 6 people at 62,500. So you take a weighted average in that case to estimate the average of the distribution, of the frequency distribution. And that's discussed here, kind of the idea. So what you would do, you would first define, so if you're doing this by hand or in spreadsheets, you would create a new column and take the average. Also, there's a typo here. It should be upper limit plus lower limit over 2. You take the average of each bin. Okay, you take the average of each bin and put it in its own column. Let me fix that since I'm here, actually. Let me just fix that. Don't work on your slides while driving. Okay, so you take the average of each bin, and we're going to call that X bar bin. Why do we call it X? Because that is the variable we're measuring. That's going to be in dollars. Remember that. That's going to be in dollars. Don't conflate that with the counts. And then you simply multiply the average for each bin, or the approximated average for each bin, by the counts for that bin. So the counts are going to be your weights, and you divide that by your summation of the weights, which is the total number of points in your data. So that's going to be n. So summation of all the counts is going to be the total number in your data set. So in this case, it's going to be 25. And I have the columns here for you. We'll do an example in Python now. But in this case, what happens? So the bin mean is 52,500, 500, 57,500, and so on and so forth. I know there's like a 0.5 and there's a $1 off. It doesn't matter. The bins, for all I care, are 50 to 55, 55 to 60, 60 to 65. We're not splitting those. But anyway, so those would be the bin means. And then the weighted mean is the product of the frequency times the bin mean. And you add all of those up, okay, and then divide by the total count, and you get 67,499. But the true mean is 67,468. So it's pretty close. Okay? So the true mean is estimated from the sample, all the data. Now, did we commit a grave mistake? Well, not really, because even the sample mean is an estimate of the population mean. Okay? And there's an error for the true population mean, which we don't know. So, using this estimate or that estimate, we're still off from the true population mean. Okay, we will quantify how far we're off once we do inferential statistics. Okay, so now if I were to give you this in Python, what would be, without looking at your slides, because there's the answers in your slides, but without looking at your slides, from what you remember, I'm expecting you learned this in numerical, what would be a smart way, quick way, to compute the bin centers? So I have an array of bins, edges, 50,000, 55,000, 60,000, etc., to 80,000. That's all you're given, and the counts, and you have the counts as well, okay? 3, 0, 6, and whatnot. How would you just do that calculation really quick in like a couple lines of code? Yes?
Probably do an iteration of each element, the I plus 1 minus 5.
So you do a for loop. You would loop over this array and say, okay, I add I and I plus 1 divide over 2, and then so on. Okay, what's another idea? Was that the same idea you had? Okay. What's a really cool and neat way of doing this iterative procedure, but in line?
You could make a bin. You could make a new array that's basically this array, but missing the first element. And then all of the other ones. Then you just add the two arrays, divide by.
So you would need two arrays, one missing the last element and one missing the first element, and you add them together.
And then
divide by 2. Okay, so how would you make those two arrays? What is that procedure called? Yes?
You could just do an array slice.
Yes, it's called array slicing. Thank you. Yep. So you saw my slides in numerical methods. I have the slides here too. But essentially you would use what we call slicing to do one shot, to do this in one shot. And with array slicing, you can access windows of the array. Okay, you can access portions of the array. Who's not familiar with array slicing? Because this is like fundamental. Okay, is the rest familiar with array slicing? Like if I tell you array 0 minus 5, do you know what that means? Okay, okay, so you're familiar with that. Okay, great. Okay, so you understand what this means, going from the beginning to the last one before last element, right? So bin edges semicolon minus 1 is going to give me 50, 55, 60, 65, 70, 75. Is going to give me the array minus the last entry. And then bin edges starting from the first entry to the end is going to give me 55, 60, 65, 70, 75 to 80. It's going to shift those two. It's going to get two windows of that array. And if I add them together and divide by 2, I get the bin centers. Okay, now, if you don't remember this, you can look at my slides from numerical methods, which I hope you've seen. And I explain kind of what the slicing is. You can go through that, but I want to get to the point where I explain to you. Okay, this is what I'm doing here. I'm trying to compute the bin centers, which I know are 55 plus 50 over 2 for the first bin center, correct? So if you think of these are the bins, bin edges 50, 55, 60 to 80. The first bin center is going to be the sum of this value and that value over 2. The second bin center is 55 plus 60 over 2. That's clear, right? But what we're doing, we're adding red arrows to green arrows and dividing over 2. Okay? What your colleagues have suggested is, and what we are doing here, what if we can make an array of the green arrows, an array of the red arrows, and just add them together and divide by 2? And you can accomplish this with the slicing. The array of the red arrows is simply bin edges, semicolon minus 1 is going to give you these, 50, 60. Yes, no, this is, sorry, they're flipped. Let me flip them again, see? The array of red arrows is bin edges. It's a window into the full array starting from 1 to the end. So it's going to give you 55 all the way to 80. And then the array of green arrows starting from the beginning to 1 before last element. And then you just add them together and you get the bin centers. The result is going to be another array containing the bin centers. It's going to be exactly the same size as your array of counts. And then you just multiply the 2, divide by the sum of the weights, and you're going to get the weighted mean. Okay, do you want me to prove this to you in Python? Should we prove it together in Python? Okay, let's do it. All right. Well, I'm going to put this on the side. Actually, I'll just create it here, because if I create a new notebook, it's going to put it somewhere else. And I remember, I think we had the salaries in some other notebook. Let me check. Then we have the salaries in the graphical descriptions of data. Yep. Yes. Okay, but now I'm just going to actually just put the bin edges. So we're going to do 50,000, 55,000, 60,000, and then 65,000, 70,000, 75,000, and then 80,000. So that's going to be our list. We can make it a NumPy array just to make sure we're just dealing with NumPy stuff. Yeah, and then we had the counts, was also a NumPy array of, we had 3, 0, 6, 4. Let me check. 0, 3, 0, 6, 4. And then 10, 1, 1. Okay? Now, sorry, this would be, I'm going to call this bin edges. Okay. And then what I claimed is that bin centers is going to be bin edges. We're going to take everything except the last element. And then plus bin edges, we're going to start from the second element all the way to the end over 2. Now, if you're in doubt, print it out. What does this give us? Add one cell here and say print bin edges. Okay, bin edges starting from the beginning to the one before last element is this guy. So 50, 55, 60, 65, 75. It stopped here, so it made an array of these guys. The second one is going to be an array of these guys. We're just going to add them together and divide by 2. Okay, so let's print the other one. Excuse me, see how nicely they line up? 50 plus 55 over 2, 55 plus 60 over 2, and so on and so forth, right? You're just adding them, dividing by 2. So that gives you bin centers. and you can print out the bin centers. Print bin centers. And you have this value. Finally, the weighted mean is going to be, we said bin centers. We want to do a summation, but first let me do bin centers times counts. Okay, so it's going to take bin center 1 times count 1, so 52,500 times 3 plus 57,500 times 0, and so on. We want to add them. How do you add them? You do, I hope you know this, numpy.sum. So you should have seen this. Yes?
I think your bin edges array is missing the last element, because shouldn't your bin edges have n plus 1 element compared to the elements?
Yeah, it does. The bin edges, 1, 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 7. That is, hold on. You are correct. So the counts should be, you're right. I have an 85,000. Sure, that's right. That's fine. It won't matter. Good catch. Thank you so much, Jesse. Okay. So yeah, just add one last entry. We just worked for just fine. Okay. But that's a good catch, because now the size of bin centers needs to be of the same size as counts. Otherwise, it would have thrown an error here, right? So now we multiply bin centers by counts. It's going to be an array of the same size as counts and bin centers. But then we need to add those up together. Okay? So we do np.sum. And again, if you don't believe me, believe Python. So print bin centers.counts. What it did, it multiplied 52,500 by 3, 0 for the second one, 62,500 times 4, and then what is it? 67,500, 62,500 times 6, 67,500 times 4. This one by 10, you see the 725,000, right? And then we're just going to add all of these up with numpy.sum. You add those up, you should have seen this in linear systems. And then we're going to divide by numpy.sum of the weights, which should be n, and of counts, and then we print the weighted mean. It's going to be $67,500, which is pretty close to what we did before. The bin edges were different in the slides, but that's okay because that's the handwritten method for the bin edges. In Python, you just do this. It's a great estimate for the mean value. Is this ringing a bell? Yep. Okay. Now that's using Python as a coding tool, not as a calculator. Okay? Like doing these slicing arrays is a very fast operation, much faster than for loops. Anytime you can slice it, because it's done at the machine level. There's no conditionals, there's no interpretation of the code. It's done at the pure memory level. It's a really fast operation. You should choose it every time you can. Okay? Bellissimo. Okay. Let's put this back here. Okay, so we'll skip these slides. And I put in the reminder slides here for you. Okay. Next measure of center is the median. And that's truly the middle value of the data. It doesn't care whether the data is skewed to the right, to the left. It literally measures where 50% of the data is on either side. Okay? It's the middle value of the data, of the counts. Okay? And you can measure that with numpy.median, and you pass it the data, just the same way as numpy.mean or numpy.average. You pass the data, and you try it out. So let's do this with the example we have. We'll count this in Python. All right, so let's go back here. Come back to the beginning. And because I want to plot the mean and the median, etc., I'm going to put mean over here is np.mean of data. And then median is np.median of the data. And let's plot them as well. So we're going to put the ax v line, plt.ax v line For the mean value, we're going to put color equal black for K for black, and then line style, we're going to put just straight, just solid line, plt.x vertical line, axis vertical line, x equal median. See where they are, color equal red, and then line style, we put dash dot. Now, how do you make your cute plot cuter? You hop on the internet or GPT and says, like, there's 1,000 options, but go with purpose. Like, okay, give it an example of, I'm trying to plot this, I want to plot a vertical line, and I want to make the color gray and make it dash dot or put a symbol on it. It will help you figure all of that out, because that's just reading the documentation, okay? So let's see. Yep. Now, notice here, we did the mean and the median are on top of each other. So the data is uniform, right? The median is going to be both the center mass and the geometric center of the data, and same for the median, right? They are on top of each other, and they will be at around 0.5 because the data goes from 0 to 1, okay? Hint, for symmetric distributions, median and the mean are going to be on top of each other. In other words, the opposite is true. When you measure the mean and the median and they're close to each other, then your data is generally symmetric. All right, so let's go down to the next one. What I'm going to do, I'm going to copy paste all of this. Copy paste. And let's just kill this guy here, all right? Okay, now we're looking at the normal distribution of the normal data set. And I'm going to plot it again. Again, the normal distribution, or these normal data, it's a symmetric distribution. We expect the mean and the median to be on top of each other. As I discussed earlier, we're going to see this a little later as well. But indeed, like, the data is well balanced. There's no mass, more mass on one side than the other. So 50% of the data is going to be to the left of whatever, 2.5, and 50% is going to be on that side. Okay, that's the interpretation of the median. The mean is going to give you, so the median is looking at the counts. How many counts you have on the right, how many counts you have on the left of that line. The mean value is looking at just the average on the x-axis. Okay, now let's do this for that last data point. You can print it and etc. I'm going to clean this up a little bit. Okay. Now this is the right skewed data. Okay, and we said that the red color is going to be the median, and the mean value is going to be in black. Now notice here we're starting to separate. Okay, because the median doesn't care if you have outliers that are trying to pull the balance to one side or another, whereas the mean is going to be affected by that. Now notice there's a difference here between the mean and the median. The mean is in black, the median is in red. The median is just saying there's 50% of the data here, which kind of makes sense because there's like, what, 2,700 points here and about 2,000 points here. There's about 4,500 points here, 4,500 data points here. And all of these bins here contain 4,500 points. Okay, good. But the mean value is saying, well, I have a very large value here. So it's going to skew the mean a little bit to this side. It's like having a bunch of salaries, you know, 80,000, 90,000, 100,000, and there's one salary that's $2 million. Then the average is going to be 1 million, right? But the median is still going to be around 80 or 90,000. And we'll do an example on that. So, and we'll see that's going to have strong implications that when the mean and the median are not close to each other, it means the data is skewed. Okay? The data is going to be skewed. Okay. The mean is not affected by outliers. What are outliers? like a feelings-based, or subjective-based description. An outlier is just a data point that's like way off. All of your data is within 10 and 30 degrees, and then 1 degree Celsius, let's say, temperature, and then one data point that's 50. Like, what the heck happened there? Sometimes you need to remove the outlier because the sensor malfunctioned, that's measuring the temp, or something was off, there was a human error involved. Okay, so you eliminate the outlier. But still, if you're given data and you're just trying to explore it, as you are reporting properties of the data, you will notice that, as I showed in the previous plot with the skewed data, that the median doesn't care about outliers. So if you add one outlier to a 500-point data set, the median is still going to be around 250, right? But if you add one outlier that's 100 times bigger in value, then the mean value is going to go way higher. Okay? I'll show you an example here. A small company employs 4 engineers who each earn $80,000, and the owner, who is also an engineer, and the owner gets $200,000. Now, the mean value, and I'm going to call that mu because that's the only population, I'm going to call that a population. And then you say, okay, 4 times 80,000 plus 200,000 over, so that's 80,000 plus 80,000 plus 80,000 plus 80,000 plus 200,000 over 5. It gives you a mean value of 104,000, okay? But that's really skewed because most people are making $80,000. There's 4 people making 80 and 1 person making 200,000. So it's wrong to say, oh, the average salary at the company is 104,000. Well, that's not really true because you need to look at the median. When you look at the median, it is still $80,000. And so in this case, you know there's a difference between the mean and the median, and you can tell that there is likely an outlier in the data. The data is skewed, is not very symmetric. And then I can ask you, and we can talk about whether you want to work for that company or not. Do you want to work for that company? Look, where I come from, I'm happy to be making $50,000. So, well, you know, there's a lot. You can go either way, right? Because you can.
How much the owner does it. The owner does a lot more, then he should get paid a lot more. But if he doesn't do a lot more, then it might be different.
Yeah, but it's also difficult to see that, right? So my friend has his own startup company here in Salt Lake. He does, I don't know if I can say what he does, but he does like some really cool, very high tech, like, you know, like not 3D printing, like 4D printing for, you know, some really fancy, I don't know what he calls it. It's like 3D on 3D printed. It's like got fractals and stuff going on. And he took a huge risk. He left his job. He had just had his second kid and on only one salary. His wife kind of essentially supporting the family, and he sunk all his time and effort into the company. He didn't make a penny for like 10 years, and he was hiring people, paying all of them, etc. And, you know, chatting with him the other day, I was like, are you finally making like $1 million a year? He's like, I'm very close. But I think he deserves every penny of it because he took all the risk, right? Put his family at risk, but made sure he can guarantee the employment of everyone. But he does a lot. So going back to your point, he does a lot. But on the other hand, you can go argue the other way. If like, oh, the employer is just this person who does nothing and just kind of trying to manipulate the system and like not paying fair wages, etc., then yeah, I wouldn't want to work for that company. So, you know, go in, understand the average. So when you look at the Glassdoor, it's going to give you the average salary, but the median is important, okay, because that tells you what most people are making at the company, okay? But also, culture and happiness matters at a company. I'd be happy making 80K, but then having, you know, enjoying the work I'm doing. It's not a toxic environment, right? Anyway, good luck with your job hunting. Okay, mode is the last measure of center. So the mode, for what we care about, the mode, bless you. Sorry, I made you laugh so much. My jokes are hilarious, so I know, Sam. Sorry. So the mode for what we care, the mode is going to refer to the peak values in a distribution. You could have one or more peak value in a distribution. We're going to call those the mode of the distribution. Formally, the mode, make me laugh, the mode is the most frequent value that occurs in a data set. And in general, we use the mode only for descriptive data, like, oh, how many red shirts versus blue shirts versus green shirts did you have? Oh, we have more red shirts. That's the mode of our shirt distribution, right? But quantitatively, it's hard to measure the mode because there are finite errors that you would make in computing the mode. So we rely on designating the mode visually when we look at distributions, okay? And that's what we will do moving forward. So you could use what's called stats from scipy.stats. You could use something called stats.mode and give it data. But you will notice that if we try this on the data that we have, it's going to give you 0 or infinity because it just doesn't work. It will only work on descriptive data like red, blue, green, lists like that, okay, or on fully continuous distributions, which we will look at later with inferential statistics. So for what we care about right now, this is not going to work, okay? This is not going to work for what we're doing, so don't use it for the data we have. Just eyeball the mode. For a uniform distribution, there's no mode because all the data are the same value. For the Bell distribution, for the bell curve, the normal distribution, it's the peak. If you have 2 peaks, not necessarily the same height, then you say I have 2 modes. There's 1 peak here and 1 peak there. You could have 7 peaks. It's a multimodal distribution. Each peak is a mode, even if they're not the same value. And although in the definition in the dictionary it will tell you it has to be equal, exactly equal, it doesn't have to be exactly equal. For descriptive statistics, just like when you see the peaks, those are the modes of the distribution. Okay? There's a sheet on how you do it in Google Sheets. You're welcome if you want to use Google Sheets, it's up to you. For the exam, you can use Python or Google Sheets, whatever is going to be easier for you, or both. Okay, I'm not going to do the examples in Google Sheets, because they're just Google Sheets. All right, for qualitative data, most appropriate measure of center. For qualitative data, only use the mode. So qualitative data, red, green shirts, whatever sizes, large, XL, medium, small, use the mode. For quantitative data, the mean should be your go-to, but if there are outliers, you should report the median. Okay, I would say report both, so you know if the distribution is symmetric or not. Here's an example of messing up the averages. This is an example from the textbook. In the 80s, the University of North Carolina reported unusually high average starting salary of graduates of their geography program. So you're looking like, oh my goodness, you know, if I go and major in geography at the University of North Carolina, they're making $500,000 when they graduate. Like, who is paying that? That's insane, right? But it turns out that the source of this inflated mean was the inclusion of, guess who? Michael Jordan, who had a geography degree from the University of North Carolina. I didn't know that. And you know, he's making $100 million, right? And so they included the salary and they skewed the data. And that is bad use of statistics. Did they lie? No, because it is the true mean. This is the money he's making, right? But he's not in geography. He's not even working in geography anymore. So, you know, that claim, like, oh, geography graduates, whatever they're working, you know, yep, we taught them basketball, we taught them how to run businesses, etc. And, you know, you got to be careful about that, okay? So next we're going to repeat what we did in Python and try to give more rigorous understanding of median, mode, and mean when we're looking at plots. And there are 3 situations. You have either a symmetric distribution, a left skewed, or a right skewed distribution. And what is that going to do to your mean and median? The mode is always going to be at the peak or peaks. If you have multiple peaks, you say, okay, this has 3 modes on it, even if they're not at the same height. Okay? So given what we know so far, that the median cuts the data exactly in the middle. There's as many counts, so the y-axis on the left of the median, as there are to the right of the median. The mean value is like a mass center. It needs to account for how much mass there is to the left and to the right of it. And the mode is going to be the peak value. So which one is which here? What do you think? So what is A? Mode. Okay. B and C, which one is mean? Which one is median? B is the median. Why? Yep. So the median is always to the left of the mean. You'll notice that. And if you're just kind of thinking about it, like the counts over here, or the area to the left of B is about the same as the area to the right of A. You're talking about counts. So B would be the median. It splits the data in half exactly. There's as many counts to the left. There's 500 here, 500 there. And the mean is going to be affected by outliers. If there's an outlier here, it's going to drag the mean. That's the $1 million example, or 100 million for Michael Jordan. It's going to pull the mean towards it. And the opposite is true if it's a left skewed distribution. So that's correct. You guys are smart. Okay. And I have this graphic from QMath. It just kind of summarizes the two. When you have a symmetrical distribution, everything is going to be lined up nicely on top of each other. Mean, median, and mode, they're going to be on top of each other. You could have a bimodal symmetric distribution where it has two equal modes, like to the left of center and to the right of center. So median and mode will be in the middle. Median and mean will be in the middle, but the modes will be on either side. And then for the right skewed or left skewed distribution, they have different names here: negative skewed, positive skewed, doesn't matter. Okay, next what we're going to talk about is dispersion or spread of the data. So the mean value, the median are measures of center. They're very simple to consider. Next, we want to think about how are these data spread? Like how far are they apart from each other? How would we measure that even? How would we measure that even? We start with what's called the range, and the range is simply maximum minus minimum of your data. So numpy.max minus numpy.min for your data, that gives you the range. We'll do the range on the next coding activity on the data we have, okay? But numpy.max gives you the maximum value in the data. Numpy.min gives you the minimum value. You take the difference, that gives you the range of the data, the extent of, like, it goes, oh yeah, these temperatures, these salaries we measured go from 50 to 85, $86,000, etc. Okay? So that gives you a sense of spread, how spread are the data. So if you were looking at the geography salaries, and you see data going from 5,000, the geography major who never found a job and they're like working at Starbucks. Not that there's anything wrong with that, versus after they spent, $200,000 in student loans, and then the $100 million, right? So when you see that spread, you're gonna be like, whoa, this is a huge spread. There's likely to be possibly maybe an outlier in these data. I don't know, but it's one thing to consider, right? The most important measure of dispersion and spread. So dispersion is a word used in math, but also can be used in fluid mechanics. Think of particle dispersion. If you inject, you have a fan and you have some incense, and you blow the fan on the incense, you're going to smell it everywhere. You're dispersing all of these particles of the incense or all of these solid particles, okay? So that's where the word means dispersion, spreading things. Variance is the key measure to measure dispersion. Okay. And we're going to approach this first visually and then come up with a numerical formula. I know you might know the numerical formula, but I like to explain it a little differently. Suppose we have these data points, okay, that forget about the y-axis for a second. We just have a bunch of, think of the y-axis as counts, but just suppose we have these data, whatever, 1 over here, 3, and then 5, and then 6, and then maybe 8 over here, 9, etc. And this is the mean value. The average is that dashed line. So it's the center of mass of the data, not the median. It's the center of mass of the data. It turns out that the best measure of how much things are spread is going to be relative to the mean value. Not the median, not the mode, not those values. It's actually the mean. Because the mean is affected by outliers, we want to measure that variability with respect to the outliers, because the outlier is also part of the spread of the system. So, but you can also argue it's just a convention. We're going to measure the spread around the mean. Now, that has important, why we choose the mean is also useful in later when we think about signal processing. If you have a noisy signal, okay, what do you measure the noise with respect to? Not the median, you measure it with respect to the mean, because that's the most likely value that's going to occur throughout the data. So the mean value is the gold standard when we're trying to just measure things relative to other things in data. So we're going to take the average value and say, okay, with respect to the average value, okay, I want to measure the spread of the data with respect to the average value. So one way we could think of, we can start taking the differences of each data point with respect to the mean. Okay, if my mean value is going to be called x bar, right, and let's say this is x1, then x1 minus x bar, I'm not putting an absolute value here yet. I can do x bar minus x1 or x1 minus x bar. It doesn't matter, whichever one you choose. That gives me a distance from the mean to each data point, right? I can repeat this for x2, x3, x4, x5, and for any arbitrary point in the data, if I take the distance from my data point to the mean, so you're essentially taking all of your original data and subtracting the mean value from it. Yeah, that's going to give you a distance from each data point to the mean. And we're looking for the average spread of the data around the mean, right? So what if we just average all of those red distances? Wouldn't that give us an average distance from the mean, an average distance of the data from the mean that we can define as a measure of dispersion? It's one way to measure the spread of the data around the mean value. Okay, so we can try to do that. So let's go ahead and say, okay, that's going to be x1 minus x bar. That's the first distance plus the second distance plus etc. We're going to add up all of those distances together and just take the arithmetic average, divide them by the number of data points or the number of distances, right? Reasonable, okay? There's a problem with this formula, and I would ask you to try to evaluate it, but you can try to evaluate it at home. Okay, so if you try to evaluate this formula, I'm showing you the math here, so you could take this and take x1 plus x2 plus x3 plus xn, put them all apart from the rest, right? And so you'd have x1 plus x2 plus x3 all the way to xn minus x bar minus x bar minus x bar n times, right? You have minus n times x bar. And then you plug in the numbers here, you're going to get exactly 0. Okay? You're going to get exactly 0. Okay? Because what you added on one side, you subtracted on the other side, unfortunately. So they all cancel out, because the mean is dependent on the values themselves, and when you subtracted and added them, they just all canceled each other out. Okay, so yes, it's an interesting measure, but it doesn't work. So you might say, let's take the absolute value. So we make sure when we're doing the differences on one side, we don't take the opposite sign on the other side of the mean. So we keep all signs positive. Okay. Now, if you do the absolute value, it does work, but it's not a good measure for statistics. We will learn some of these properties later, unfortunately. So you have to kind of trust me on this. But one key reason why we don't use the absolute values is if we define our variance based on absolute values are discontinuous at 0. Okay, when they change sign, they are discontinuous. So we cannot use calculus to take derivatives and do true inferential statistics. So we need a quantity that is nice and continuously differentiable. So the next best thing that we can think of that still gives us a positive value, okay, but is not subject to the issues of the absolute value is what? Is the square. What if we take the squares of those distances, and just sum them up and take the average of those squares of the distances? Later we can take a square root to make it the same units, but the same dimensions as our variable, but that would work. And the square is a nice continuous, it's going to give us a nice continuous distribution. It has some really neat properties. And also reminds us of what? Well, how do you measure the length of a vector? Exactly, you add up the square. What is the L2 norm? You remember your L2 norm in numerical methods? When you measured the length of an array, right? The length of a multidimensional vector that has 15 dimensions. Pythagorean theorem. That's what you're doing here. You're just adding up the squares of the distances. Now you take the average of that. In the Pythagorean theorem, you don't take the average, but that's the idea. So I'm just saying this to tell you that it's not a strange idea to think about an average distance or a total distance as the sum of the squares, because you do it all the time to measure distances with vectors. Okay? So let's do that. If we do that, then we get x1 minus x bar squared plus x2 minus x bar squared and so on squared. And those do not cancel out. And then we define what we call the variance. Bear with me here. I have an n minus 1 in the denominator, and that is not a typo. That thing I know for sure it's not a typo. Okay? And we're going to call this quantity s squared. We're going to call that the variance. It's the sum of the square of the distances from each data point to the mean value. Okay, we're going to divide that by n minus 1. We'll learn why n minus 1 a little bit later. But this is going to be our definition of the variance. And the variance, we're going to claim that variance measures how much spread your data is, how much spread there is in your data. Now be careful. This is a square measurement. So the units, the dimensions of this are going to be square of x. So if your x are salaries in dollars, the variance is going to be in dollars squared. That's weird, right? If you're measuring degrees Kelvin, it's going to be Kelvin squared. Okay, it's going to be variance is going to be dimensions squared. So it still doesn't really make intuitive sense. But once we take the square root, we're going to bring it back to the true dimension, and we're going to call that the standard deviation. But the true quantity, we start with the variance, is this guy. Now, why do we prefer the squares? The absolute values, I said, are non-differentiable at 0. The variance, turns out, is directly tied to what we're going to call the expected value in probability theory and in probability distributions, and is directly connected to the normal distribution. So it turns out that the normal distribution can be derived by minimizing these distances. You can say, okay, if I minimize this, what distribution do these data belong to? You derive the normal distribution from that. Now, historically, that came much later, much after when people developed all of these. But you can see kind of how like things are the product of their times. Like there's a certain maturity in the science, in the math, and like people are surprised. Oh my gosh, AI! We were ready for AI. Like I said last time, you have 10,000 pictures every day you take. You cannot sort through that. No system is going to sort through that. No Google Photos or Apple Photos. You need AI to sort through that. So we needed that. It's the product of our time. So same thing here. Okay? And with that, I'll be done. Godspeed. I'll see you on Thursday, and we'll finish this up. Okay? Thank you.